Welcome to this next video in the playlist on topology. In this video what we're going to talk about is what is meant by the standard topology on the set Rn. Okay, so the structure then for this video, I'm going to start off by reminding you of the definition of a topological space. I'm also going to remind you of the informal intuition for what a topology is actually doing. Then what we'll do is we'll discuss what Rn is as a set, and we'll discuss the motivation for the standard topology on Rn. Then what we'll do is have a look at the rigorous actual definition of the standard topology on Rn, and finally we'll come back and understand why this rigorous definition of the topology on Rn actually fulfills the motivation for what we were trying to achieve. Okay, so firstly then, the reminder of what a topological space actually is equal to. So a topological space starts off its life as just being a set of symbols. So I'll start off by drawing just a set of symbols here. So this box here, this is going to denote a set containing lots of symbols. Okay, so it'll be full of symbols, full of elements, and at the moment this is just a set of symbols. It has absolutely no other structure on it at all, it's just a set of symbols. What we now want to do is define a topology on this, and once you've done that, this set will now be elevated to the stature of a topological space. Now, what does this structure of a topology actually try to achieve? Well, the motivation for what we're trying to achieve with the notion of a topology is we're trying to achieve a notion of what is next to what is connected to what else. At the moment, this is just a set of symbols. There is no notion of elements in this set being next to other elements in this set. Okay, so intuitively what we are trying to do is draw little lines between elements of the set to mark whether they are connected, whether they are next to each other or not. Okay, so intuitively, the way I would urge you to intuitively think about what you're trying to do with a topology is if we've got two elements of the set here, A and B, then what we might want to do is, if we want to show that those two are next to each other, we might like to draw a line in between them, like so. So the informal intuition behind what you are doing with a topology is that you're drawing lines in between elements in the set to show which elements of the set are next to other elements of the set. So if you draw a line in between two elements, you've shown that those two are next to each other. Okay, now, that's the informal intuition behind what we're trying to do, define a notion of what is next to what by drawing these lines. Now let's have a look at the rigorous definition, and then we'll try and understand how the rigorous definition can be viewed in this way with the informal intuition. Okay, so the rigorous definition then of a topology, which is usually denoted tau, is that it's a subset of the power set of the set capital X. Okay, now the power set of the set capital X is the set containing all subsets of the set capital X. So absolutely all subsets of this set capital X will be elements of the power set of X. So what that means is that our topology tau is going to be a set that contains lots of subsets of the set capital X. Okay, now, the topology tau cannot just be an arbitrary set of subsets of the set capital X, however. It has to obey some really important properties, and we discuss these properties in far more detail than I'll go through them here in the previous video in this playlist on topological spaces, but I will just remind you of them now. Okay, so the three properties that we insist that this set tau must obey is property number 1 is that the empty set and the entire set capital X must be in tau. Okay, they are both subsets of the set capital X, trivial subsets of the set capital X, but still subsets, and we insist that those two subsets must be in our topology tau. In addition, the second property that we're going to insist on is that if you take any two subsets of your topology, and I think actually I'll try and write these down, so I'll just put them quickly here. So property number 1 is that the empty set and the entire set capital X must be an element of tau. Property number 2 is that if you pick two arbitrary subsets of the set capital X that are in the topology, Okay, so we'll denote them U1 and U2. So these are both subsets of the set capital X that are in our topology. Then it must also be the case that U1 intersect U2. The intersection of these two subsets is also an element of tau. Okay, and that must hold true for all U1 and U2 that you can possibly pick. So that means that you have to pick the elements that are going to be in your topology very carefully, because as soon as you have two elements put into the topology, it has to also be the case that any intersection of those two elements also has to be in the topology. Okay, so you have to define this thing very carefully. Axiom number 3 then, the final property, says that you can union together an arbitrary number of sets from the topology and you will still end up with another element of the topology. So this index alpha can be whatever index you like. It can be a countable index, it can be an uncountable index. You can union together an arbitrary number of sets from the topology, so all these U alphas are from the topology capital tau, and you must always end up with another element in the topology. So the topology must be closed under intersection, a finite number of intersections, and it must be closed under an arbitrary number of unions of elements of the topology. Okay, right, so those are the 3 properties that we insist that this topology must obey if it's going to count as a topology. If it's going to have this stature of being called a topology, it must obey those 3 criteria. Okay, right, so that's a reminder then of the abstract definition of what a topology is. Now let's try and, what I want to do now is remind you of why this corresponds to the informal intuition. How can you use this to actually do what I was saying is the informal intuition behind what we're doing with a topology? Okay, well, the way that you can do it, and this is informal, but this is a useful intuition, and you'll be surprised how useful this is. We can use this intuition to motivate a huge number of definitions in topology, some really important ones. For instance, the definition of a continuous function, we can motivate it completely with this informal intuition. So although it is an informal intuition, it's a very, very useful intuition. Okay, so how then do we go from this abstract definition of a topology to actually drawing lines in between elements of our set, the more intuitive notion of what a topology actually means? Okay, well, the way that you can decide whether 2 elements of the set are going to be next to each other, whether they're going to have lines drawn in between them, is you go to your topology tau and you ask, is it the case that whenever one of these elements, A or B rather, appears in a subset that is in the topology, is it always with the other one? Okay, so I'm going to draw a line in between A and B. I'm going to say they're next to each other, they're truly next to each other, if it's the case that whenever one appears in a subset that's in the topology, the other has to appear in that subset as well. Okay, so they can never appear apart, they always have to appear together if I'm going to draw a line between them. So if I can find a subset that has only one of them that's in the topology, then that's a no-no. You don't draw a line between them. They're not next to each other. They're only going to be next to each other if for every single subset that's in the topology that contains one of them, it also contains the other. They only ever appear as a pair in a subset in the topology. Okay, so that's how you can use this abstract notion of what a topology is to go back to this more intuitive picture. And beware, this isn't completely rigorous. This is an informal intuition, and it works for beautiful finite sets. You can easily define this for finite sets, but when you get onto infinite sets, it becomes more difficult. But still, it's a very powerful intuition, and it will help us motivate a lot of the definitions for topology later down the line. Okay, right. So that's a reminder of topological spaces then. Now let's go on to the meat of this video. Let's address the standard topology on the set Rn. So what we need to start off with is, what is the set Rn? Okay, so the definition of the set Rn then. Okay, so this is just going to be the set of real numbers Cartesian producted with itself n times. So this is just a set theoretic definition. I'm not doing algebra here, I'm not doing geometry, I'm not doing anything apart from set theory. Okay, I'm using the fact that the real numbers is a very, very complicated set of symbols, fundamentally. It's just a set of symbols. Yes, the rigorous construction is horrendous, but it is just a set of symbols, so I can do set theory with it. Okay, so what I'm going to do is I'm going to take the real numbers, and I'm going to Cartesian product it with the real numbers, and I'll continue doing this n times. So I will take n lots of the real numbers and Cartesian product them all together, so there are in total n lots of these. Okay, so let's now write this out completely, okay, explicitly. What is this set going to actually equal then? Well, it's going to end up being the set containing all n tuples of real numbers. So explicitly written out, what are the symbols that are going to be in this set? Well, it's going to be all n tuples of real numbers. So we're going to have x1, x2, all the way along to xn, like so. So we're going to have all of these symbols where xi's are elements of the real numbers. And again, I will stress that this is just a set at the moment. I know these things look like vectors, okay, it's because we use the same notation for them. But at the moment, I have not said that I want to define any algebraic structure on this at all. Okay, so do not think of this as a set of vectors. It's just a set of n tuples of real numbers. I'm just doing set theory here, not algebra. Okay, right, so that's what fundamentally the set Rn is actually going to be equal to. Now, to motivate the standard topology that we're going to put on this, the first thing to say is that this set can have a huge number of different topologies put on it. The standard topology is one topology that you can put on the set Rn. However, there are loads of other ones. It's by far not the only one. Okay, and as far as abstract maths is concerned, there is nothing special about the standard topology whatsoever. Okay, it's only special because of the real world. It's only special because we believe that this set with the standard topology on it, in the case that n is equal to 1, 2, and 3, mirrors the topological structure of the one-dimensional continuum, the two-dimensional continuum, and the three-dimensional continuum, respectively. That's the only reason we're interested in this. That's the only reason it's given the grandiose title, the standard topology. Okay, as far as maths is concerned, it's not that special at all. It's only special because it mirrors, well, we believe it mirrors the real world. Okay, so firstly, let me just state how many different topologies there are on here. So let me just illustrate the fact that you can put loads of different topologies on this. So for instance, in the video on the topological spaces, we saw two topologies that you can put on any set, the chaotic topology and the discrete topology. And Rn will certainly take those topologies. So remember, the chaotic topology is where the only two subsets of the set that you put into the topology are the empty set and the entire set itself, so the two that have to go in. And that's always a topology for any set capital X that you have. So it will certainly be a topology that we can put on the set Rn. Okay, so there's a topology that we could put on Rn which isn't the standard topology. In addition, we could put the discrete topology on Rn, and in the discrete topology what you do is you set the topology tau equal to the power set of X. You put in absolutely every single possible subset of the set capital X. Now that doesn't even bear thinking about in the case of this massive great set, but in principle you can do it, okay, and that will also obey these three axioms that the topology needs to obey, and that's called the discrete topology. Okay, so certainly we can have more topologies on this than just the standard topology, and it's very important to appreciate that this isn't the only topology that you can put on Rn. It certainly is not the only topology that you can put on Rn. Okay, right. So, now then, why are we actually so interested in this? Well, of course, the motivation for this is that we are trying to build a structure, a topological space that mirrors the topological structure of real spaces in the real world. So the real one-dimensional continuum, the real two-dimensional continuum, and the real three-dimensional continuum. Okay, and to actually draw a picture of this, I could do it for all three. I could do it for the one-dimensional continuum, the two-dimensional continuum, and the three-dimensional continuum. The three-dimensional continuum is difficult to draw. It's difficult to draw three-dimensional pictures, and the one-dimensional continuum is a bit boring. So we'll go in the middle. We'll go for R2. So I'm I'm going to illustrate the intuition behind what we're going to do with R2, and it will be generalizable to R1 and R3, and I hope you'll easily be able to extend it to R1 and R3 once we've discussed it for R2, and then mathematically we can extend it to Rn. We don't need to limit ourselves just to 3, we can go 4, 5, 6, etc. And we believe that if we were to live in a 5 or 6 dimensional continuum, that their topological structure would be the same, or it would be mirrored by the topological structure of these abstract mathematical spaces that we can construct. Okay, but before we go on to that, let's just have a look at what we're actually trying to do here. Okay, so let's take set R2 here. Okay, so the set R2 will be all pairs of real numbers, so that's simplified it hugely. We've gone down from n real numbers just to 2 real numbers, so we've got pairs of real numbers, so the xi's are real numbers here. Okay, now this set is very special because what we can do is associate the points in this set with the two-dimensional plane. Okay, so let me illustrate this. So what we're now going to do is we're going to associate the points in this set with the two-dimensional plane, and we're going to do this in the normal way that you did for years and years in school. Okay, so here is my picture of the two-dimensional plane then, and what we can do is we can imagine dividing the two-dimensional plane up into a nice grid like so. So we'll have the origin here, so that point in the two-dimensional plane will be associated with the symbol 0, 0, which is from my set, and what we can continue on doing is imagine dividing it up into a grid, and as I say, you have done this for years and years in school without thinking about it, like so. And then what we can do is associate points on this two-dimensional grid, this way of dividing up the two-dimensional plane, with points in this set, with elements in this set. So for instance, this one might be given the symbol 1, 0, this one might be given the symbol 0, 1, this one will be given the symbol 1, 1, and I don't know why I was saying might be given, we're going to give them these symbols, etc. Okay, so I hope you understand what we're doing here. We are associating all of the points on the two-dimensional plane with a symbol back in our abstract mathematical set here. Okay, now of course, there are other ways that you can associate the symbols in this set over here with the points on the two-dimensional plane. This is certainly by far not the only way that you can do it, and in more advanced maths it becomes important that that's not the only way that you can do it, but let's do it this way because that's the most intuitive way of doing it. That's the way we've been happiest with doing it for years and years and years. Okay, so we'll stick with that, the Cartesian way of associating these symbols from this set with the points on the two-dimensional plane. Okay, right. Now, here's the motivation for what we're going to define then on this set. The plane here, it has a topological structure. It has a notion of which points in this plane are next to other points. Okay, at the moment our set here has no topological structure, it's just a set of symbols. What I would like to do is equip this set with a topological structure, with a notion of which symbols are next to which other symbols in this set, such that it mirrors the structure here, i.e. such that points that are next to each other here, the symbols that represent them in the set here are next to each other in the set. I want to create this into a mathematical structure that mirrors the two-dimensional plane in its topological structure. That's what I'm trying to do here. I'm trying to create an abstract mathematical structure that mirrors the two-dimensional plane here. Okay, so you might be wondering, well, what is the sort of topological structure on the two-dimensional plane? Well, here's where I'm going to use some informal intuition, give you some informal intuition. So this isn't going to be rigorous at all, but this is my informal intuition for the topological structure on the two-dimensional plane. Okay, so if we take a point then in our two-dimensional plane, so let's have a point here. What points on that two-dimensional plane are next to that point P? Well, this is a difficult question because which points are going to be next to it? Which points can I draw little lines between this point and those other points? Okay, well, it's very, very difficult because you can always get closer. Okay, so which points do you really want to say are connected or next to this point? Okay, well, the intuition, and this is sort of like the intuition that everyone uses for calculus when they first learn it, until they learn analysis, and then they have their intuition scrapped and they end up with the rigorous account of it. My intuition for the topology on this is that what you need to do is zoom in and in and in and in and in on the plane, and zoom in forever and go one step further, zoom in forever and a day. Okay, so zoom in beyond what you can ever zoom in to the infinitesimal scale, and then intuitively, if you could zoom in to the infinitesimal scale, what you would then see is a grid that looks like this. Okay, so a little grid like this, where these points on the grid are the points of the plane. Okay, so these are going to be points of the plane here, and these lines in between the points of the plane, these are going to be the little lines connecting those points. Okay, so intuitively, this is my intuition for the topology of the plane, that if you were to zoom down to the infinitesimal scale, you'd eventually see infinitesimally close points connected to each other by lines like so. Okay, in this beautiful grid-like array. So here, let's say this is our point P here again, in turquoise, like so, and then these other points here that are around it and connected to it, these will be the points that are infinitesimally close to it. Okay, once we've zoomed into this level. Now I know that that's not a rigorous account of what this means, but intuitively that's the way that I picture the topology of the two-dimensional plane, that if you were to zoom in infinitesimally, you just have this incredibly ordered array, an incredibly ordered square array, two-dimensional square array like so. Okay, and what we are now trying to do is equip this set with the same structure. Okay, so we're going to try and put little lines between these pairs of real numbers that are infinitesimally close to one another. Okay, so what I want to do is, if I've got the symbol in here that's representing P, then I want to put lines in between that symbol and the symbols that are representing these pink points, which are infinitesimally close to it. So I'd like to try and get a topological structure on here that mirrors the topological structure on there. Okay, and of course, you can imagine generalizing this. This is the picture for R2, or and I should say, this is what's going to be the standard topology on this set R2, a topological structure that mirrors the topological structure of the two-dimensional plane. That's what's meant by the standard topology on R2. And of course, this concept can be generalized for other Rn's. Okay, so for R1, what we'd want to do is put the topological structure on that is going to mirror the one-dimensional continuum. So here's the one-dimensional continuum. What's the topology of the one-dimensional continuum? Well, again, imagine zooming down, 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 down to the infinitesimal scale. Then what you can imagine you'd see is an array of infinitesimally close points like this, where they are connected to each other by little lines. Okay, so you just end up with a string, beads on the string of infinitesimally close points, all connected to each other, all next to each other. And what I'd like to do is take the set R1 here, which of course is just the set of all real numbers, xi, where xi's are real numbers. Okay, and I'd like to connect them up, okay, in a way that mirrors this. So I'd like to take this real number that represents this point here, P, and connect it to the real numbers that represent these two infinitesimally close points here. And you can imagine also doing this for R3. Okay, so in R3, if you zoomed in, what you'd end up with is little cubes. I'm not going to even try to draw that because I can't draw in 3D. Okay, but you'd end up with an array of little cubes where the points were infinitesimally close to one another. And again, what I want to do is try and create a topological structure, create a topology that's going to connect these symbols in the set R3 that represents those infinitesimally close points. Okay, and then we can imagine generalizing this to Rn as well, once we've got an abstract mathematical way of describing this topological structure that's going to achieve this. Okay, so the standard topologies then on Rn, these are just topological structures that we're going to put on these abstract sets so that overall they mirror the topological structure of real spaces. Okay, at least that's the definition for R1, R2 and R3. Of course it becomes more difficult when we go higher, but we can still do it. We can still make it as an abstract mathematical definition, because as I say, we are going to come up with an abstract mathematical way of capturing this, okay, and that can truly be generalized up to Rn. Okay, so what we'll do in the next video then is we will look at this abstract mathematical definition for the standard topology on Rn, and then right at the end we'll come back to R2 and we'll have a look at why this abstract definition of the standard topology that we can put on R2 is actually going to imbue it with the topological structure of the two-dimensional plane, or at least what we believe is the topological structure of the two-dimensional plane.